Okay, it is with great trepidation that I go on to discuss 6.1 in Gregory on semantics and interpretations, the semantics of predicate logic, aka quantificational logic, also known as quantification theory. And this is the toughest section in the book. So if you don't get it, don't worry about it because it is really, really tough. It's very abstract. So that's the bad news. The good news is you get a little bit of a homework vacation because I'm not going to ask about anything in connection with this particular section. We'll go on to 6.2 and 6.3 where things are a little bit more concrete, and then I'll have some worksheets for you to do. But right now, wow, this is the theory of it. And this is really, really tough stuff. And after this is over, I'm going to have a stiff glass of sherry and binge watch Call the Midwife. Okay, here we go. 6.1, and this is pages 201 to 216 in Gregory. Okay. Whoa, why is this not working? Whoop, whoop, okay. So I'm breaking it down section by section. There's a lot more in the text than is in this PowerPoint. So you really need to go through this, look at the examples, and work through it. Okay, what is an interpretation? So Gregory starts you off in a relatively gentle way by giving you a rough and ready informal understanding of what an interpretation is. And this follows in what we've been discussing about translation, for example. And by the way, give me some time on acknowledging, if I manage to do that, the homeworks that you sent me, because it's quite a big deal for me to get them acknowledged, get them filed away, and respond to your questions. So just bear with me. I'll try to do that. I'll try to do that stuff tomorrow. Okay, interpretation of P, where P is a language of predicate logic, quantificational logic. And as I say, this is an informal account just to get you started. Okay, an interpretation of P. Let's see if I can get some pointers here. Laser pointer, yeah. Can I get another color now? Whatever. An interpretation of P consists of three components. First of all, there's the universe of discourse, UD. And sometimes I slip and I call that universal domain, which is another way of describing the same thing. But what the universe of discourse is a non-empty set of things that we're talking about. Okay, and we'll give examples presently. So that's the first thing. That's the universe. That's what we're talking about, the universe for the purposes of our discussion. Secondly, an interpretation consists also of an assignment of truth values or natural language statements, when we understand it in this informal way, to statement letters, and also of natural languages predicates or extensions to predicate letters. So we have an assignment, truth values or natural language predicates or extensions, right? That's the second component. The third component concerns the denotation of constants. So an interpretation in P consists, informally understood, consists of an assignment of objects from the universe of discourse to constants via a translation key, such that, in other words, we're assigning objects to names because constants are names, okay? And we assign them in such a way that every individual constant is assigned to an object, which is to say there are no empty names, right? There are no names like the present King of France. Every constant is assigned to an object. And second of all, the names are not ambiguous, which is to say no individual constant is assigned to more than one object, okay? Now in natural languages, sometimes there are names that are shared by lots and lots of people. And my thesis supervisor was named George Wilson, and that apparently is the second most common male name in the United States. So trying to look him up in the phone book when I once tried to do this in graduate school was pretty close to impossible because there were like 3 pages in the Baltimore phone directory. But that's not the way things work for an interpretation of P. Every individual constant is assigned to an object, and no individual constant, no name, is assigned to more than one object. Okay, so far so good. Now, Gregory also gives us an informal, a rough and ready account of what satisfaction, how we are to understand satisfaction and truth in P in the language of predicate logic. Okay, here we go. And remember, these doubled letters are metavariables, right? So F is just some predicate or other, and X is some variable or other. It's just a placeholder for some variable or other. Okay, given an interpretation where Fx is a woof with only instances of the variable X free, what's free mean? Well, it means it's not bound by a quantifier. Okay, it's just there. And A is a constant. Here's how it works. The denotation of A constant, satisfies, so this is a definition of satisfaction. The denotation of A satisfies Fx, or we can also say alternatively, Fx is true of the object named by A, if and only if Fa is true. In other words, A satisfies Fx if substituting the name A, right, the constant A, for X results in a true sentence. Okay, so that's relatively straightforward. Okay, for example, right, take being bald. Suppose that's the predicate, right? And suppose we're considering Socrates, who is bald, right? Now, the predicate is bald, right? Is satisfied by Socrates because it's true of Socrates that he's bald. And we'll get on to more about Socrates in a bit. Now, clauses 2 and 3 are about quantified statements, right? Universally and existentially quantified statements. So 2 concerns universally quantified woofs of the form for all x fx. And such statements are true if and only if the condition expressed by the immediate subcomponent fx, this bit, is satisfied by every object in the universe of discourse. And that makes sense, because if you're saying, what should we say? Everything is material, right? For all x, x is material. Well, that's true, right? If being material is satisfied by every object in our universe. An existentially quantified woof, it's also intuitive. There exists an x such that fx is true if and only if the condition expressed by fx, the immediate subcomponent fx, is satisfied by at least one object in the universe of discourse. What should we say? There exists an x such that x is a philosopher, right? An existentially quantified woof. Is that true? Well, it's true if is a philosopher is satisfied by at least one object in the universe of discourse. And if the universe of discourse is human beings right now, then it's true, because there's at least one human being like me and others, but me is good enough, that satisfy being a philosopher. Okay, so this is the informal account of satisfaction and truth in the language of predicate logic. Okay, so let's consider an example. And the moral of this story is, remember, we have an account of what an interpretation is. It consists of a universe of discourse. It consists of an account of what it is for sentence letters to be true and for predicates to have an extension. And also the third component of it is it consists of an assignment of constants or names to individuals in the universe of discourse. So let's see how this works. Okay, and here's the thing to think about, which we'll come back to presently. Truth, the truth of any woof, is relative to an interpretation. Okay, so let's consider the following interpretation. The universe of discourse shall consist of ancient Greek philosophers. Okay, the set of ancient Greek philosophers. Then we have a bunch of predicates. We have a one-place predicate being bald, and Gregory is using the circled ones and twos as placeholders here, right? We can't just have blanks because order matters, as is the case for this two-place predicate, teaches, right? So one teaches two is not the same thing as two teaches one. We want to say that the first item is going to be the teacher and the second item is going to be the student. But going back, okay, so we have these predicates. We have one-place predicates, is bald, H for is human. Then we have a two-place predicate, teaches, such that the first item is the teacher and the second item, the second position, is filled by the student. Okay, that's the second component. We've got predicates. And then the third thing we've got are constants, names. And we'll just say A names Aristotle, P names Plato, and S names Socrates. Okay, now that's the interpretation. Now let's make an assumption, right? An assumption about the way things are. Let's assume, and this seems pretty safe, that all ancient Greek philosophers are human. Let's assume also that Socrates is bald, right? And let's assume that Plato is not bald. Now, what we're interested in is what that interpretation does for a number of woofs, for woofs 1 through 5. Okay, we'll take 1. Socrates is bald. Baldness is a predicate that applies to Socrates. Well, that's true, because Socrates is in the extension of bald things. That's true of Socrates. In other words, Socrates satisfies B1. What about 2, BP? Well, P is the name of Plato. And to make this true, Plato would have to satisfy the B predicate, but Plato does not, because Plato is not bald. So BP on this interpretation is false. How about the universally quantified statement for all x, hx? That's to say, for all x, h is human. Okay, well, let's check what we've got in the universe of discourse. We've got ancient Greek philosophers, and we agree, we assume that they're all human. So every object in the universe of discourse satisfies the is human predicate. Therefore, 3, the universally quantified sentence is true. Going on. There exists a y such that by. There's something that's bald. Well, let's check. Let's check what we've got in the universe of discourse. Well, it's ancient Greek philosophers. And among those ancient Greek philosophers, we have got Socrates, and Socrates is bald. So that makes for true. There exists a y, there exists an object such that that object is bald. True. Okay? But now let's go back again and let's consider the universally quantified statement for all z. Z is bald. Well, let's check. Within our universe of discourse, which is the set of ancient Greek philosophers, we've got Socrates, but we've also got Plato and Aristotle, and we agreed that Plato is not bald. So it is false that for all z is bald. Okay, because remember, go back, let's see. Yeah. Okay, the universally quantified woof for all x, fx is true if the condition expressed is satisfied by every object in the universe of discourse. And when it comes to being human, every object in that universe of discourse, ancient Greek philosophers, satisfies that claim. On the other hand, to an existentially quantified statement, there exists an x such that fx, and that's true if we have at least one. So we have at least one individual, namely Socrates, who's bald. So there exists an x such that there exists an X such that bald X or bald Y or whatever, that's true because we've got Socrates. But it's not the case that everything in our universe of discourse satisfies that predicate, so that's false. So that's the picture. And Gregory gives you a lot of other examples that you can work through, but the idea here is that truth is relative to an interpretation. And if we change the interpretation, what if the universe of discourse consisted of all mammals? Not just all Greek philosophers, but all mammals, including dogs and cats and all that stuff. Well, on that interpretation, for all X, HX would be false, right? Because there will be individuals in this revised universe of discourse that are not human. Again, okay, so changing the universe of discourse, right? Getting an interpretation with a different universe of discourse can change the truth value of woofs because they're interpreted differently. Again, suppose we knock Socrates out, right? We don't have anything that refers to Socrates. We don't have anything like that. Well, then we're not going to have anything that's bald. So when we change the interpretation, we change the truth value of the various woofs. We're not talking about the same things. Okay. Now, this is an intuitive definition, but as Gregory notes, it has some shortcomings because we want something more general. We want a semantics not just for singular statements and for quantified statements that only involve one predicate. We want, our language is richer than that, so we want a definition of interpretation that will cover all the cases. And that's when things get complicated. Okay, because informal definitions only handle one-place predicate letters. They don't explain how to handle, first of all, relational predicates, right? Like that teach predicate, we didn't have anything going in that last example about teach 1, 2. We have to have an account of that. And it will not do if all that we can talk about are individuals, because if we have a two-place predicate, and this gets us back to a little bit of set theory, then we construe that predicate not as a set of individuals, but as a set of ordered n tuples. And if it's a two-place predicate, it's a set of ordered pairs. If it's a three-place predicate, it's a set of ordered triples, and so on. So we have some work to do when it comes to relational predicates. And I'm just underlining instead of putting circles, because I do not have the capacity to do circles. Okay, so we're going to need ordered n tuples to make this out. Secondly, we did not get rid of the truth functional connectives from propositional logic. We still have them. So we still have, within our language P, sentences that involve connectives, right? Truth functional combinations. And we need our semantics to take care of sentences like that. Sentences like, for example, excuse me, FA and FB, or FA implies FB, and so on. Or similarly, sentences involving quantification and also connectives. So we've got some work to do there. Okay, we need a definition of satisfaction for such sentences. Finally, we need an account of satisfaction and truth for quantifier variable constant combinations like the ones here. For all X, there exists a Y such that Fx and Hy, etc., etc. So we've got some work to do, and the work is hard work. Here we go. Okay. In addition, right, further shortcomings to investigate the quantificational logic properties of woofs of our language P, we don't just want to consider one interpretation, but we want to consider what happens to the truth value of a woof or woofs on all interpretations, right? Because remember, going back to chapter 3 on propositional logic, that a truth functionally true woof of our language S, the language of propositional logic, is one that is true on every truth value assignment, logical truth, tautologousness. So we have comparable properties when it comes to the more complex language of predicate logic, a parallel, the more complex concept is that of quantificationally true, logically true, but not tautologous, but logically true in virtue of structure. When we say that a woof is quantificationally true, right? If it's true on every interpretation of P, of our language, okay? And then there's a further wrinkle, because we note also that the universe of discourse can be infinite. And it's useful to be able to talk about infinite sets, because suppose we want to talk about all natural numbers. The universe of discourse could be n, right? The set of all natural numbers. So we need more. And that's why the informal definition, the intuitive definition of truth and satisfaction needs to be expanded. We need a fix to get these more complex kinds of woofs interpreted. Okay. Now, this is just a little bit of review because, and this is the section in Gregory on a little bit of set theory, because we talked about set theory already. And this is where the stuff hits the fan. This is where we really need that set theory. Okay, so just to review, just repeating, in case you forgot, a set is a collection of objects, right? And we call the objects that belong to the set the members or elements of the set, okay? Recall that we have different ways of specifying sets. We can specify them by enumeration, right? Listing them, Socrates, Plato, Aristotle, or using ellipsis, 1, 2, 3, whatever, to specify the set of natural numbers, 0, if you're inclined to call that a natural number, or January, February, ... December, right? Which is a way of specifying the months of the year. So we can specify sets by enumeration. We can also specify them by description. For example, the set of natural numbers, right? So that's another way of specifying this set. Months of the year, that's another way of naming this set. And finally, and this is, I suppose in some ways the most maybe familiar, it's familiar to me, we can specify a set by set builder notation, okay? So consider this set. We pronounce this as the set of X such that X is greater than 1. Okay, so that means all numbers greater than 1. Or alternatively, this is just, I mean, the bar here is just a notational variant of the colon. Sometimes you see that too. So this is also read, the set of X such that X is greater than 1. Okay, so this is just notation, right? In terms of the theory of sets, we have identity conditions for sets such that a set S is identical to a set S prime if and only if S and S prime have exactly the same members. So remember, when we're talking about plain old curly bracket sets, order doesn't matter. All that matters is having exactly the same members. And we had on one of the quizzes, I think I gave you a little bit of an exercise on the identity of sets. Now, also remember, and this also figured in that exercise, we also talk about sets of a special sort, namely ordered sets or ordered n tuples. And the notation for that we're using right now is we're using plain parentheses instead of curly brackets to indicate that this is a set where order matters. An alternative notation, and for some reason this figures quite often in logic books, though that's being changed, is pointy brackets. This is just an alternative notation for the parentheses that signify order matters. We're talking about ordered sets. And when it comes to ordered sets, the ordered set X, Y, Z is not the same as the ordered set Y, Z, X. They have the same members, but more is required for order sets for their identity conditions. Namely, they have to be in the same order. Okay, so more review about sets and their members. And this is more terminology. The E stands for element of or member of. X is a member of the set S, right? Is indicated by this. And if we want to say that X is not a member of the set X, we can just put a slash through that. but don't confuse set membership with set inclusion. Set inclusion is about the subset relation. And we designate proper inclusion, right? Where S is included, is a subset of S prime, but it's not all of S prime. We say then that S is a proper subset of S prime, okay? So in this case, S is not the same as S prime. We can also talk about subsets, whether proper or improper, right? It could be, S can be a subset of S prime, or it could be identical to S prime. And we say that S is a subset of S prime if every member of S is a member of S prime. And of course, that goes for S itself, because every member of S is a member of S. Okay, so distinguish set membership from set inclusion. And once again, I think Gregory has a reasonably illuminating discussion of that. And of course, what sorts of things can be members of sets? Well, everything. Sets can be members of sets. So here we have a set that consists of one and another set, namely the set of 2 and 3. So you can have a look at that. And then, of course, some sets, well, I shouldn't say some sets. There is a set that has no members, namely the empty set, and that's designated either by the curly brackets with nothing in between them or this symbol. Okay, so this is just terminology that we need in order to use set theory to understand what's going on with the semantics of predicate logic. Okay, now at the very end of this section, Gregory briefly talks about the idea of a function, and this is also going to figure in our discussion of the semantics of predicate logic, because there are a couple of functions involved in setting up the semantics, namely the extension function, which maps names to objects in the universe of discourse, and which maps predicates to sets. We also have a denotation function, which figures in connection with variable assignments. So we need to know what a function is, and we've been there and done that, remember? A function takes inputs, more terminology, that are called arguments, and nobody is exactly sure why. It's called arguments, but that's what they're called. And for each argument, for each input, it yields a unique output called the value of the function at such and such, or called the image. That's just terminology. The argument goes in, the value comes out, the image comes out. That's it. Okay, so now we have the machinery. Wow. So now we have the machinery to set up a more formal definition of truth and satisfaction for predicate logic. The formal interpretation of the language P. So this is 6.1.3. And when you see this, you're at, uh-oh, okay? And as Gregory notes, if the level of technicality in this section is intimidating, feel free to skim it to get the gist and then move on to the next section on constructing interpretations. And it's the stuff on constructing interpretations that you're gonna have homework about. But before we get there, have a look at this stuff. I'll go through it as best as I can, but all I can say at this point is don't panic. Okay, now why will you panic? It's because there are all these symbols, right? Okay, function E, we talked about functions, and then you have all this stuff that looks terrible, like you have these letters that are superscripted and subscripted, and you have all of these symbols, and on it goes, right? You have the set theoretical notation, a set of these ordered and tuples. Okay, and I'm going to go through each bit of this in the next screens, one bit at a time, but I'll start looking at this and then I'll go through each bit, one bit at a time, okay? I understand this because I have been afflicted by really terminal math fear, and as soon as I see all the subscripts and the superscripts, my eyes are out on stalks. Okay. So remember, we have a rough and ready notion of what an interpretation is in an informal way. So now let's just get more detailed about it. As I said, part of an interpretation, one feature of an interpretation is the universe of discourse. a non-empty set of the objects that we're talking about. Okay, so that's straightforward. Okay. Now we have a function E, the extension function, that assigns extensions to predicate letters and objects to constants, such that, okay, first of all, here's a clause for sentence letters, right? These are zero place predicates. So the subscript just says this is a zero place predicate. In other words, it's just a sentence letter, right? And the subscript isn't doing anything at all. It's just giving you a way of having more predicates than the 26 letters of the alphabet. So you can just ignore that, yeah? So if F is a sentence letter, a zero place predicate, right? Because sentence letters are just zero place predicates, then the extension of F0 sub K, right, is an element of a set that consists of just two objects, the true and the false. In other words, with the extension of a sentence letter is just a truth value when we've only got two of them, true and false. Okay, so that's pretty friendly. No problem there. Okay. Now, suppose we have a predicate, an n-place predicate, right? Well, if F is an n-place predicate where n is greater than or equal to 1, in other words, it's not just a sentence letter, there's one or more terms following the F, then the extension of F is a set of ordered n-tuples, right? How big are these n-tuples? Are they pairs or triples or whatever? Well, however many n is. So the extension of Fn, of that predicate, is a set of n tuples. This one, and so on, right? Where every object, right? Where every object involved is a member of the universe of discourse, because we can only talk about what we're talking about. And once we decide this is our universe of discourse, everything that we talk about has to be in there. Okay. So this is a little bit complicated because remember, once again, one of the problems with the initial informal interpretation is that we didn't have any way of dealing with relations with more than one place predicates. And this gives us a way of dealing with relations now that we have the set theoretical apparatus to do it. Okay. Now, C, this clause is pretty straightforward. If C is an individual constant, a name, right, a constant, then the extension of C is some object within the universe of discourse, right, something that it names. Whew. Okay, now it gets a little bit more complicated because we're not just interested in the extensions of sentence letters, predicates, and names, constants, but we also have within our language variables. So we also have to talk about variable assignments. That's to say, a way of assigning objects to the X's, Y's, and Z's. Okay, here we go. A set A of all variable assignments, little a. So little a is a variable assignment, a way of assigning objects to variables. And big A is a set of all those ways of assigning to variables. The set A of all variable assignments, little a, in which every variable, every individual variable, X, and the double X is just a metalinguistic expression of the language, is assigned to an object in the universe of discourse. So here's a set theoretical representation of it. What is A? What is that set of all variable assignments, right? A is the set of little a, the set of little a's, such that the A of a given variable, right? The variable assignment for a given variable X is an object in the universe of discourse. Again, the universe of discourse is all that we can discourse about. So it's going to be an object that's in UD. Okay. Now, We're distinguishing, remember, interpretations. And we're referring to interpretations as M for model. And an interpretation, remember, is something that assigns truth values to sentence letters, to predicates, n-place predicates, sets of ordered n tuples, and to constants, to names, individuals. So that's what M is, right? Okay, it's that model. But in addition, because we've got these variables kicking around, and we have to deal with variable assignments as well as the extension of these other items, right? We say, for an interpretation M, and each variable assignment in that set of variable assignments, we define yet another function, the denotation function. Okay, so this says the denotation in interpretation M on variable assignment A. That's how you read it. The denotation, this is a function, the denotation in interpretation M given variable assignment A. It assigns objects from the universe of discourse to individual terms of P in the following way. Okay, and T is just a variable, a metalinguistic variable for term. And what are terms? Well, there are two kinds of terms. There are constants or names, and there are individual variables. So there are the two possibilities. If T is an individual constant, C, then the denotation in M under variable assignment A of T is just the extension of C, right? Doesn't matter what the variable assignment is because there are no variables around, right? We're just talking about a constant. So D M sub A of T is the extension of C. Okay, the extension of C. Okay, well, what if T is an individual variable X? Okay, well then denotation in interpretation M under variable assignment A of T, right, is the assignment, the variable assignment to X. Okay, so I'll go over these bits one bit at a time. This is an overview, and let's see what we can make of it. And as I say, if you're completely baffled, you're normal, because this is the toughest stuff in the book, and it's extremely abstract, but it's worth going through. And then we'll get to more concrete stuff. Okay, so let's begin. Okay, clause 1. What's the universe of discourse? It's a non-empty set, right? What is the function E? Well, that's the extension function. It takes in symbols, right? It takes us from symbols to objects, including sets. That's the extension function. And how it works in particular, to repeat once again, there are 3 cases. It could be that what we're dealing with is a zero-place predicate, so-called, which is to say a sentence letter. So sentence letters go into the extension function, and the output is a truth value, whether true or false, right? It takes in sentence letters, spits out truth values. That's the extension function. What if predicate letters of more than 0 place go in, right? That was the second clause. If F n sub k is an n-place predicate, yada, yada. Okay, well, if something like that goes in, then a set of either individuals or ordered n tuples comes out. If it's a 1-place predicate, a set of individuals comes out. If it's a relational predicate, 2-place, 3-place, whatever, then a set of n tuples comes out. Finally, and this is fairly straightforward, if a constant letter goes in, right, then an object from the universe of discourse comes out. The object that constant names. Constants are names. Okay. Okay. Let's continue on with the third clause. And this is the one that's baffling and complicated, difficult. Because remember, within our language, we don't just have names, we have variables. So we have to consider variable assignments in our interpretation. Okay? Okay, so the set A of all variable assignments, lowercase a, okay, lowercase a is one of many variable assignments in which every individual variable x sub I of P is assigned to an object in the universe of discourse. In other words, what's A? What's A? It's the set of variable assignments, little a. A is a set of variable assignments such that the assignment to any variable x, is an object in the universe of discourse. Okay? So A designates the set of all variable assignments for some universe of discourse. Now, what exactly does a variable assignment look like? Okay, well, it's an infinite sequence of objects from the universe of discourse. Objects, right? These are the things in the universe of discourse that we're talking about. Okay, and each of the variables designates in a variable assignment, each of the variables picks something out, right? One to one, because we can't have any of these not referring to anything, and we can't have them referring to more than one thing. So on one assignment, V picks out object 1, W picks out object 2, X picks out object 3, and so on. That's just one variable assignment. Things can be scrambled around in another variable assignment. Okay? So that's the other function we've got here. We've got the variable assignment function. We've got the denotation function. Okay. Continuing on with our understanding of formal interpretation of the language P. For any interpretation M, and each variable assignment A within that set of variable assignments, we define a denotation function. Remember, we talked about that function, right? The denotation function in interpretation M under variable assignment A that assigns objects from the universe of discourse to individual terms. And once again, two kinds of things are terms. There are names, constants. And when the term in question is a constant, the denotation in interpretation M under variable assignment A is just the extension of C. Right? If it's a name, then that's it, the extension. If, however, the term in question is an individual variable, x, then the denotation function, the denotation in interpretation M, variable assignment under variable assignment A of that thing, right, is the object assigned to that variable on that variable assignment A. Okay, so this is the second time I've said it, but it takes a lot more to get this thing in. So as I say, it might be helpful to look at the book. Okay, so let's review what's going on here. D, that function name designates a function that assigns objects from the universe of discourse to terms. That's to say, constants or variables in interpretation M in a variable assignment A. So we've got two things going here. We've got the interpretation, the stuff about extensions, and we've got the variable assignment in question. So for a constant, the extension of C and the interpretation of M, okay, that's it. For a variable X, the object assigned to X, right, is what the variable assignment tags it with. Okay. Now, oh God. Now that we have an understanding of this notion of an interpretation, we can define the notions of satisfaction and truth in our language P. Okay, so this is a somewhat less intuitive notion of satisfaction, because we have to expand that intuitive notion of satisfaction to accommodate all of these other cases that we need to deal with. Okay. So suppose we've just got a sentence letter. It's a zero-place predicate. Okay. Then a variable assignment A satisfies that sentence if and only if the extension of that sentence is the true. Remember, all that this function does when it inputs sentence letters is it spits out a truth value, whether true or false. So a variable assignment satisfies the sentence if the extension of the sentence is true. Okay, that's satisfaction for sentence letters, for the simplest sentences. Okay. Now, suppose F is a predicate that is of more than 0 places. In other words, it's a 1 or 2 or whatever place predicate. It's not just a sentence letter. Well, then, depending on when n is, it's going to be followed by n terms, whether variables or constants or a mix of both of them, right? So if P is a sentence of this form, right, a predicate followed by the appropriate number of terms, then a variable assignment satisfies that sentence if and only if the denotation in interpretation M on variable assignment A, right, of this whole thing, right, the denotations of term, right, is an element of the extension of the predicate where, as I say, it's a 1 or more place predicate if the following holds. Okay, so here are the clauses, right? Thirdly, the third clause, and this is pretty straightforward. Okay, so here what we're saying is that we have to have these items, right, in the extension of the predicate, right? The third clause concerns the way in which we deal with connectives that carry over from propositional logic. And this is really straightforward, right? Suppose P and Q are woofs of our language P. Well, then a variable assignment satisfies not P if and only if that variable assignment does not satisfy P. Okay, that's straightforward, right? That's negation. Again, a variable assignment A satisfies P and Q if and only if both A satisfies P and A satisfies Q, as we would expect. So without going through all these clauses, you can see that what we have here is an intuitive account of how the connectives figure in our language of propositional logic in terms of variable assignments. Okay? Now, the last two clauses concern quantified expressions. They concern sentences that involve quantifiers, and this is where it gets a little bit stickier. Okay, suppose P is a sentence of the form for all x, f something or other, followed by the appropriate number of terms. Okay? In this case, for the universally quantified sentence, a variable assignment A satisfies that sentence if and only if every other variable assignment A prime that's different from A in at most just one place, right? Just the A prime of a given X, right? At most a given X satisfies the sentence in question, okay? If every way of replacing one bit of the variable assignment with something else from another variable assignment, right, satisfies. As you might imagine, when it comes to the existential quantifier, we don't need everything to satisfy. We just need that there be one variable assignment that only differs in one place. We only need one, at least one, that satisfies. So this is how we define, and as I say, the kicker is the stuff about variable assignments is difficult, right? So this is how we're going to assign, this is how we're going to understand in a rigorous way the notions of satisfaction and truth in our language P. Okay. Now, going through this a bit at a time, because it takes repetition and it takes spinning it out. Given an assignment M, giving an interpretation M, satisfaction is a relation between a variable assignment A and P, a woof of the language. So for all variable assignments A and all woofs P of P, first of all, if P is a sentence letter, then that variable assignment A satisfies P if the extension of F, right, is true. So that's simple. Second clause, if it's a one or more place, if it's a one or more place predicate, then a variable assignment satisfies if the denotation of each of the terms in variable assignment A is a member of the extension of the predicate in question. Okay? So for a sentence letter F, A satisfies F if and only if the extension of F is the true. For a predicate letter followed by one or more terms of FT, A satisfies FTS if the object or objects in the universe of discourse assigned to the T terms by the denotation function is or are in the extension of F, okay? So as I say, you really have to read this. You can't understand it if I'm just talking about it, so I'll keep talking about it, but you really got to read this to make sense of it. Okay. Then there were the clauses, and I think this is very straightforward. Then there are the clauses that deal with the connectives that carry over. So we're interested in variable assignments, right? And this is intuitive because we still have those connectives, so we can define them in that way. So rules for the satisfaction of sentences involving connectives are, go in terms of the satisfaction of their parts. Okay, so this just follows from our understanding of the connectives. Then when it comes to the quantifiers, once again, right? Clause 4, a variable assignment A satisfies for all X, F followed by a term or terms, okay? If and only if every variable assignment A prime that is like A, except for what's assigned to the variables following F, satisfies. And in the case of the existential quantifier, we just need it to be the case that some variable assignment like A, right, that just exchanges one item, right, will satisfy F. That's all we need. We only need some for the existential quantifier. We need all for the universal quantifier. Okay. Okay, now for truth. What is truth? Well, truth in our language, truth in P, is going to be defined in terms of satisfaction. Okay. So a closed woof, that's a sentence. A closed woof has truth value. A closed woof P of our language is true on an interpretation M if every variable assignment A satisfies P on M. Okay, that's how we're going to understand truth for the purposes of this system. Okay, what about falsity? Well, a closed woof, that's to say a sentence P of our language, is false on an interpretation M if no variable assignment satisfies P on M. So if every variable assignment satisfies, it's true. If no variable assignment satisfies, it's false. Okay. So let's see. Sentence letter. What is it for a zero place predicate, a sentence letter, a statement letter to be true? Well, it's true if every variable assignment satisfies it, okay? Because there's nothing, it doesn't have any variables, right? Right? So it's just plain true, and we just define it to be the case that every variable assignment satisfies it because it's just plain true. In other words, there are no variable assignments that fail to satisfy it because it doesn't have any variables in it. Okay. Now, what about an atomic sentence that involves only constants? Remember the difference between atomic and molecular sentences. Atomic sentences didn't involve any operators. It didn't involve any connectives, and it also didn't involve any quantifiers. Now, such a sentence is true if and only if the n-tuple of denotations of constants is in the extension of the predicate. Okay, I'm going to see if I can come up with an example. I think I'll have an example presently. So let's just sit with that for the time being. What about a sentence involving connectives? Well, remember that clause we had? So the idea here is that if not P is satisfied, if and only if P is not satisfied, this kind of thing. So the stuff on connectives is pretty straightforward. It's truth functional, no problem. Quantified sentences, true if every variable assignment satisfies it. What about open woofs? Remember, these are ones that just have variables hanging, not bound by any quantifier. Well, such items, open woofs, do not have truth value. They're neither true nor false. Only sentences, only closed sentences or closed woofs have truth value. So that's how we define truth in the language P. Okay, now, one thing that Gregory stresses, and rightly so, is that truth value is relative to an interpretation, because letters and symbols, they don't have any inherent meaning. They don't have any intrinsic meaning. You can make them mean anything you want. And by assigning an interpretation, you're assigning a meaning to them. But by themselves, the marks don't mean anything. So truth value is relative to an interpretation. So let's consider some possibilities here. And in other words, what's going on here is, the interpretation involves different components. It involves a universe of discourse. It involves a stock of predicates. And it may involve an assignment to constants. Okay, and changing anything like that around makes a difference in whether a given string of symbols expresses a truth. Okay. So let's consider this interpretation. The universe of discourse is natural numbers, and some say begins with 0, some say begins with 1, doesn't matter, okay? The predicate P designates the set of primes, and the predicate E designates the set of even numbers, right? So on this interpretation, there exists an X such that PX and EX is true, which is to say there exists a number which is both prime and even, and that's true. Number 2, the only one. Okay, but what if we interpret things differently? Okay, what if we say that the universe of discourse, once again, we keep that the same, is natural numbers, and once again, P designates a set of primes, but now we're going to make E designate a set of 2 numbers that begin with the letter E, 8 and 81. Okay, so we've changed the extension of the predicate E. Well, now this is false, because now we've said there exists an X such that it's an even prime, but we don't have any in here. Okay, the only objects that are E are 8 and 81, and neither of them is prime. Okay, what about over here? Let's change things around in another way. Suppose, in this case, once again, the universe of discourse is natural numbers, and we have a greater than or equal to predicate. So this G designates the set of x, y, such that x is greater than equal to y. And now we have a constant, we have a name, O, and that's a name for 1. So let's see. For all x, O is greater than x. Well, no, because it's not the case that O is greater than all those natural numbers. So that's false. But what if we restrict the domain? What if we restrict the universe of discourse to just one object, 1? Okay? And so now, in this case, in the first case, we change the extension of one of the predicates. In this case, we've changed the universe of discourse so that it includes just one lonely number 1. And we keep the predicate greater than or equal to the same. And once again, O designates 1. Well, everything in the universe of discourse, namely 1, is greater than equal to 1, right? Because the only thing we got is 1, and it's equal to itself, so that will do. So the moral here is that if you change the interpretation, either by choosing a different universe of discourse, as is the case here, or by changing the extension of one or more predicates, as here, or for that matter, don't have an example of it, but changing what names name, right? You can change the truth value of a string of marks, as indicated here. Okay. Oops. Okay. So now let's consider what's involved in constructing interpretations. Okay. And what we're interested in, and this is the kind of problem that you will be looking at. And as I say, there's a little bit of a homework hiatus, right? Because what I'm going to be asking about will be constructing minimalist interpretations. So that's going to be into next week when we talk more about this in 6.2 and 6.3. Okay? You want to construct a minimalist interpretation to make a sentence true or false. Okay? And he has some instructions on how to do this kind of problem. He also notes that you don't have to worry about being fussy, because instead of saying the set, the ordered set that consists just of A, the ordered set that consists just of B, you can just say ABC, and so on. And you specify the universe of discourse for this kind of problem, right? And I'll try to give some examples by using the relevant constants, where we understand constants to denote arbitrary objects, okay? Once again, to repeat, every constant that appears in the relevant WOOFs has to appear in the universe of discourse. It has to name something. It can't just be an empty name, like the present King of France. Secondly, we're not going to explicitly interpret the constants, right? We're going to say they denote whatever they denote. So B denotes whatever B is. We're not going to commit ourselves to B denotes Bernie Sanders or B denotes any other individual. We're going to say that B denotes whatever B is. And then finally, unless explicitly stated, unless we say, for example, A, unless we specify that A is identical to B, we're going to assume that each constant denotes a unique member of the universe of discourse. Okay, so those are the rules for constructing an interpretation. Okay, how does this work? Okay, so we've got these two sentences. Remember, these are like the translation sentences in the homework. And by the way, give me some time on acknowledging the homework and getting back to you about it, because I've got quite a bit of this stuff and I have to, because it's not automated, so I have to respond to each one individually, saying I've got it, and respond to any questions I get. So that's going to take me a little while. So we're probably looking for tomorrow, at which point I will also have at least my solutions to homework 4, sorry, I'll have that up. Okay, so we've got these two sentences. There exists a y such that for all x, right, L, y, x. There exists a y such that for all x, y loves x. And then we have this one. to use the stock example. There exists a y such that for all x, x loves y, okay? So this one says there's someone that loves everyone, right? This one says there's someone, some y, who's loved by all those x's. So that's the difference between these two things. And let's see what interpretation it takes to make them true. Okay, in this interpretation, and he uses M for an interpretation because another way of talking about it is as a model, okay? So this particular model has as its universe of discourse the set A, B, C, D, okay, just like the other one. And we have a definition for the L predicate for loves, such that it consists of the ordered pairs CA, CB, CC, and CD, okay? Now, well, let's look at 3. 3 says there's someone who loves everyone. Someone who loves everyone. Well, look at what here. There's someone C, right? And C loves A, C loves B, C loves himself, and C loves D. So 3 on this interpretation is true because there's someone, namely C, that loves everyone. But 4 is false because what does 4 say? It says there's someone who everybody loves, but there isn't any such, right? There isn't any such. A is not loved by A or B or D. B is not loved by A or B or D, okay? So on this interpretation, and as I say, I'll put the PowerPoint up as soon as I'm done with this so you can chew it over and also look at the examples because it takes a little bit of thinking to figure out what's going on here. Okay, what about, so that's how things work given this interpretation. But what about this interpretation, right? Where we have the same universe of discourse, but we define the L predicate differently, such that it consists of a set of ordered pairs AC, BC, CC, and DC. Okay, now on this interpretation, 3 is false because what does 3 say? It says there's somebody who loves everybody, but there isn't anybody who loves everybody here. A just loves C, B just loves C. All of them just love C, right? There's nobody that everybody loves. However, consider 4. So as I say, this is an example, an interpretation to make sentences true or false. And here are the sample sentences. There exists a Y such that for all X, right? There exists a Y such that for all X, X loves Y. Okay. For all X, X loves Y? Sure. Okay. There exists a Y, there exists a Y such that for all X, Y is loved by X. Okay, so all the X's love C, right? So on this account, given this interpretation, given this way of understanding the predicate L, 4 comes out true. Okay, so that's the kind of example that we're going to be working with. And that's what, in particular, the problems in 6.2 and 6.3, which are somewhat less abstract, deal with. So having been through the abstract stuff about defining an interpretation, applying satisfaction in P, we can get down to specifics, which are more comfortable. Okay, because when we go onward, and now I'm just looking ahead, because this is the material in 6.2 and 6.3, we'll be talking about the semantic properties of woofs and sets of woofs and coming up with interpretations to show, for example, that a given woof is logically true, or that a given woof is not logically true, or that a set of woofs is consistent, and so on. And this is what the problems are going to look like. So looking ahead, I won't do it now, because this is what I'm going to do next time when we get on to 6.2, because that's what we're going onward to. right? So if you look at the exercises, they will ask you to construct minimalist interpretations to show, for example, that a given woof is not quantificationally true, not necessarily true, right? And this is the kind of thing, so I'll just go through this because we're not going to do it now. We're going to do it next week. And this is the stuff that you're going to do looking ahead. And I haven't finished the PowerPoint for next time, but you can just look here to see where we're going. And this is what the exercises are going to look like. And this is what the homework for next, which I'll give you next week, is going to look like. Blah, blah, blah. And that's it. Okay. Wow. Okay. So this is the theory behind it. What we're going to be doing as we go on to 6.2 and 6.3 is we're going to be constructing minimalist interpretations, and I will have some worksheets and some homeworks for you. So you don't have to worry about having to do something about this theoretical stuff, right? It's nice to understand it because this is the underpinning. This is what's behind what we're doing. Okay. But for now, I will leave you for the weekend. As I say, tomorrow I will try to have responded to your homeworks and to acknowledge your homeworks. And I hope I get to that. As I say, it's not mechanized. And I'm also going to put up the solutions. I'll create the solutions for homework 4 so you can see. And I should also note something about homework 4. I came up with solutions for the 2 proofs, and somebody else came up with other solutions that were perfectly correct. So if you're doing a proof, there could be a lot of different equally correct solutions. So don't worry about it. If yours doesn't look like mine, I'll check it over and I'll see that it's okay. Okay? So happy weekend. And as I say, I'm now going to relax and binge watch Call the Midwife. Okay, happy weekend. And let me stop this.